I hope in the last lecture I could impress upon you that in metamorphic rocks you can identify multiple fabrics, and the fabrics have formed at different times. So if you could now correlate the timing of a mineral growth with respect to the fabrics, then you can find a time relationship between the formation of the different minerals. Because the fabrics represent certain times, if we can relate a particular mineral with a particular fabric or between two fabrics, then we have an idea as to when the particular mineral or the set of minerals formed. And this is a very common way of doing things. Let's start with one, and I hope you remember that minerals have different strengths. Mica schists offer more slip, so more of the simple shear component is accommodated to the micaceous layers. The quartz feldspathic layers, they accommodate more of the pure shear component, and there are certain minerals which are very stubborn and they occur as major like obstacles to the flow path of deformation of rocks. Now we will study that in, this is what I call mineral matrix relationship. Now let's start with a particular texture. There are three types of textures that can be distinguished, and this requires a lot of confidence, and for that you need to really look at many rocks, understand them, understand how minerals and fabric relations are correlated. It takes experience. So we have different types of mineral matrix relationships. And so you have something called pre-tectonic porphyroblasts, pre-tectonic minerals, post-tectonic minerals, and syntectonic minerals. Now when I say tectonic, I am saying because these fabrics are called tectonic fabrics, metamorphic foliations, these are called metamorphic fabrics. So this tectonic word that is used now is a very common usage, it is used all over. Pre-tectonic means pre with respect to certain fabric, syn with respect to certain fabric, and post with respect to certain fabric. And normally there is a term that we use, is called a porphyroblast. Porphyroblast. And there is another term which is called blastoporphyritic. Blastoporphyritic. Now you remember from your igneous texture, a particular texture that we discussed is called porphyritic texture, where a particular mineral is larger than the matrix. So it is that same term porphyro. That means porphyro, this means this we are talking of a mineral which are somewhat larger than the minerals in the matrix. Now there are two terms, blastoporphyritic. Blast represents some sort of a deformation metamorphism situation. So blastoporphyritic means the rock was of a porphyritic texture. That means the rock was initially had an igneous texture that was deformed. Have you understood? Blastoporphyritic mineral means there is or could be an igneous mineral which has been later deformed, and obviously its shape etc. have changed. So that is called blastoporphyritic. And porphyroblastic, porphyroblast or normally it is porphyroblast. porphyroblast. Porphyroblast is a mineral that is a metamorphic mineral that has grown during, predating, during, and synchron post-dating a particular metamorphism. Have you understood? So there is a connotation difference between blastoporphyritic and porphyroblastic. Porphyroblastic essentially refers to a metamorphic mineral, and it could be syntectonic, post-tectonic, pre-tectonic. But blastoporphyritic, porphyritic is originally an igneous rock which has been deformed. So the deformation postdates igneous processes. But porphyroblast has got nothing to do with igneous rocks. It has got nothing to do with sedimentary rocks. It's a purely metamorphic term. And normally this is referred to a mineral which is larger than the matrix. So first, in order to understand, we will understand this texture first. Post-tectonic. What does it mean? So, let's say, let me draw a sketch. Say, this is, I give it a term, SI. S, the word S in metamorphism or in structural geology is related to a foliation plane. Have you understood? S represents a foliation plane. This should be SE and this should be SI. SE means external foliation. SE means external foliation. External to what? External to this larger view. And SI, it is also a planar fabric, but it is internal to the mineral. And this mineral is a porphyroblast. And this mineral is a porphyroblast. So what we see here, we see a fabric, a metamorphic fabric, which we call SE, and the fabric continues and there is no deformation, metamorphism, it is just a continuous fabric, and you grow a mineral and you see these are some small sums, these are called inclusion trails. These are called inclusion trails. So what we see, what is inclusion? This mineral, in order to form, it must have formed. This was there before and the mineral must have formed later. So obviously there was a reaction where matrix minerals, this is the matrix, reacted to produce a porphyroblast. So that is the metamorphic transformation that has happened. And how this has happened? This porphyroblast, you see, has no deformation, evidence of deformation. These fabrics just continue as such without any bending or whatever it is. And you can see that SE, external fabric, continues inside as an internal inclusion trail. Now, inclusions are all residual minerals. Residual minerals. That means residual minerals. What are residual minerals? So minerals here reacted to form this mineral, and the residual minerals, say for example, you have A 50%, B 30%, and C 20%, out of which A 30, B 50, and C 50, in this proportion it has reacted to produce D, which is the porphyroblast. So what has happened? Because you see A 30, B 50, C 50, so obviously when this reacts in this proportion, but the minerals are there in this proportion, you expect C to consume first, and you will have leftover A and B. So where will this leftover mineral grow? They stay there. These are the residual minerals that form the SI trails. So these are also called inclusion trails. So A is present in the matrix, A is present, A50, B30, C20, but reaction is 50, A30, B50, C20, C50. So obviously C will react out first because the proportion of C is more and it produces D, but then A and B will remain. They will be the residues left from the reaction. But since they already had a preferred orientation, so these mineral trails also show a preferred orientation. So here, Si, the inclusion trails within the porphyroblast, is continuous with the external fabric. This can happen when the porphyroblast is post-tectonic. So this is a classic example of post-tectonic growth of D through a reaction between A and C. And that porphyroblast grew after this fabric. That means the mineral growth post-dates is later than this fabric. Gives you a time frame. So this mineral is younger than this fabric. So this is what is called a post-tectonic fabric. Say for example, you see, that's a classic example of post-tectonic fabric. This mineral grew after this fabric was folded. After this fabric was folded. It was not this mineral, which is a porphyroblast, a rigid mineral, this mineral was not there before. It overgrew, it post-dated the folded fabric. So these are examples of post-tectonic growth of minerals. Now let's study a little bit. These you can hunt on the internet and post-tectonic porphyroblast, and they will give you wonderful images. You will have wonderful websites which give you very good examples. I am giving one or two examples, but there are different ways in order to identify post-tectonic porphyroblasts. Now I talk about pre-tectonic porphyroblast, which grew before effoliation. And this looks typically like this. Let's say this is a porphyroblast, let's say this is garnet, which is very rigid and strong, and you have a foliation that warps around it. Have you understood? This is a typical example of a pre-tectonic porphyroblast. That means this is SE, external foliation. There may be no internal foliation, but you can see the foliation warps around the garnet, means the garnet was there when the foliation developed. The garnet was there when the foliation developed. And these are these triangular parts here. These triangular parts here. These parts. These are called strain shadows. These are called strain shadow zones. Strain shadow zones. What happens when you have a garnet porphyroblast? If you have seen, I don't know whether you have seen, during rainy season, for example, if you have water flowing and if you keep a brick, you will see the brick occurs as an obstacle and the water flows by, and on that side you will generate a triangular area where the flows meet, and there you have a zone where it is triangular. So these are pressure shadow zones. In pressure shadow zones, these are shadows in the high strain zones. Have you understood? These are low strain zones and these are high strain zones where the materials have sort of flowed around it. But as it flowed, the ones in the shadow of the garnet, those preserved. These are the areas where you can look for early fabrics. Early fabrics. You can look for early fabrics here. And the early fabrics may have been destroyed in these parts. These early fabrics may have been destroyed in this part because of tremendous amount of flow of material. So early fabrics, as I've shown you before, the early fabric may be completely obliterated and destroyed. But in this pressure shadow zones, often you find early fabrics preserved. Early fabrics preserved. Now, say for example, this is a typical example of a pre-tectonic porphyroblast. A pre-tectonic porphyroblast. If you can also have such a situation where you have a garnet and you have some sort of a fabric like this and this. You can have a situation like this. What does this say you? What does this say? This is the S external and this is SI internal, but there is also another SI here. There are two SIs. There are two internal foliations. Here you see, you have a garnet where there is an inclusion trail like this, which is oblique, and this internal foliation is like this, and it is surrounded by another garnet, a mantle of garnet, which does not preserve this internal foliation. But these margins of this garnet, you can see there are inclusion trails. And these inclusion trails are at high angle to these inclusion trails. Means what? And you can see the foliation has sort of walked around it. What does this mean? This means there can be complicated ways, but a very simple ways, that this part of the garnet was pre-tectonic with respect to the matrix foliation. This internal tail in the core of the garnet grain is at high angles. That means it formed in a different orientation and then was warped by a later matrix foliation. But that you find inclusion trails here, it means that this part is a later overgrowth on an early overgrowth mantle over an earlier grown core. So this is it. This indicates two generations of garnet growth. An earlier growth that formed, these are inclusion trails. These are formed from a matrix which was at a different orientation than the present metamorphic matrix, the core part. That the foliation warps around it. But the foliation warps around it. But then you can see this part of the garnet, the outer rim of the garnet, that has grown to beautiful euhedral shapes, idioblastic shapes, and the SI trails here are continuous with the SE trails. That means this is pre-tectonic with respect to the matrix foliation, and this is post-tectonic with respect to the matrix foliation. So here you are. You can have a mineral with complex histories. So that means a part of the garnet grew before the matrix foliation and the outer mantle grew after the outer matrix had warped around the older garnet. So you can have porphyroblasts with multiple histories. But you see a very interesting feature. This inclusion trail here, which is oblique to the external matrix, you don't see this in the rock. You may not see it in the rock. You might only see it preserved in the garnet porphyroblast. That means, as I have told you before in the last lecture, that earlier fabrics in the rocks can be obliterated. Yes, but if there is garnet or a rigid mineral porphyroblast that has grown before, that will preserve its early history. Here, you don't see this fabric at all. You don't see this fabric at all. So that is a very, very important observation, that minerals grow over time relating to generation and regeneration of fabrics. So it gives you a good handle to find out how minerals can grow in time as newer and newer fabrics are imposed on the rock. So we have talked about post-tectonic porphyroblast, pre-tectonic porphyroblast, and a combination of the two porphyroblasts. Okay? So these are the... It's not easy. You have to get acclimatized to all this. Most of these things require a lot of experience, but they can be done. It's not that they cannot be done. That's the important point. Now, we come to this. Now, I can tell you one thing. Those who have worked a lot in my career on rocks. In geology, it's very easy to find out what is early, what is late. That is relatively easy to find out. But one of the most difficult things in geology is to find out if two events occurred simultaneously or contemporaneously. Say, a fabric forming, a mineral forming. If it is pre, it's easy. If it's post, it's easy. But how can I say that the mineral grew when the fabric formed? Now, these are all very, very complicated questions. And some of these textures that I am showing you, these are convincing. But syntectonic textures showing syntectonic growth of mineral is one very, very tricky thing. I will show you the one that is generally agreed on by 90% people. And then I will draw a few diagrams where people have said, no, this is not syntectonic. Another set of people have said, no, this is post-tectonic. So a lot of complications. But first I will show you something which conclusive, and more than 90% people accept that, okay, if you see such textures, it means syntectonic. Now, This is an interesting texture. There are several important things you must remember here. This I have drawn as a garnet porphyroblast. With inclusion trains. And this is the matrix inclusion train or the external schistosity. And this is the internal metamorphic foliation or internal schistosity or whatever, or internal cleavage, whatever you might like to say. You can use it at the moment. You don't have to be so stringent. The important point here is you can see this internal inclusion. These are curved. I'm drawing it, yes? Please don't mind. These are curved this way. Can you see? These are curved this way. And these are curved the opposite way. I can draw another texture that I drew before. This was SE and this was SI. Now you can see here something. Now here the external foliation is V-shaped. External foliation is V-shaped. There is no prominent pressure shadow. There is no prominent pressure shadow. But there are these triangular matrices, and these are the external matrices. The important point here is, here these lineations are curved this way, and here the lineations are curved this way. They are oppositely curved. Here, they just run parallel. Have you understood? And this fabric does not show any deformation, or any perturbation, or any disturbance, because of the growth of this mineral. Now this is taken to be an example of syntectonic growth of minerals. Syntectonic growth of minerals. This is taken as one of the best examples of syntectonic growth of minerals. Now, how does this texture happen? So essentially, you had to start with a small nucleus. So you start with a small crystal, and then you have a foliation that goes over it. And then the mineral grows simultaneously, and then also the foliation develops around it. And then you have the foliation growing over it, and the foliation warps around it, and again the foliation warps around it, and then the mineral grows over it. Do you see that? So this mineral here has grown simultaneously with a fabric that has grown over time, of course. Every fabric grows over time. So this mineral here shows growth rings like this, where a mineral is there is a warping fabric, mineral overgrows the warping. So here what happens, you start with a mineral, and then you have a foliation. So the mineral is pre-tectonic with respect to the warping foliation, but then the mineral overgrows it. Have you understood? So the mineral is growing and the fabric is forming. Have you understood? The mineral is growing and the fabric is forming. So what is happening, as the fabric is growing, so is the mineral growing. So this is what happens when you have a syntectonic porphyroblast. So this is taken to be one evidence of syntectonic porphyroblast. It has, in fact, it has the features of both pre and post textures. both pre and post. Why pre? Because the foliation warps around this. So there is a tendency for it to be the porphyroblast, that part, to be pre-tectonic, whereas the foliation crosses over the mineral growth. So there is also a post-foliation growth effect. So essentially, the syntectonic is a combination of pre-tectonic growth, foliation development, overgrowth, foliation development, overgrowth, foliation development, overgrowth. So the mineral continuously grows as the fabric grows. So this is taken to be an example of syntectonic porphyroblast. So what I am trying to impress upon you, that in a rock where you have multiple fabrics are showing, you can have porphyroblasts that grow at different times during the growth of that fabric. And you can constrain in relation to the fabric when the mineral has grown. So then there is an example of porphyroblasts that show this type of textures. Many people have said this is syntectonic texture because here you have the SI, here you have the SE, and SI and SE are continuous within the fabric. So one says there are some people had said, some people think that these are syntectonic growth of minerals, but others say no, it's not. It's completely rubbish. Why? Because they say that you have this fold, and then I grow a garnet like this, which means he's talking of a post-tectonic growth. Here also, all the features that I show here, SI, SE continuous, this is SI, this is SE, all these are continuous, all the features can be shown. So people are highly debated whether this and this texture are post-tectonic fabric, post-tectonic features, or syntectonic features. So these are some of the doubts that remain. But the texture that I showed you, that is one texture that is taken to be a classic example of syntectonic growth of minerals, starting with an early form minerals and growth of fabric and growth of mineral simultaneously. So now we can see, and another thing is, therefore you can see when a new mineral forms, obviously the minerals in the matrix, they react to produce the new minerals. They react to produce new minerals. So obviously, new mineral formation means the pressure temperature condition of the environment has changed. So it is our business now to find out how does the pressure temperature change, and how the pressure temperature change is related to the tectonics of the area. Now, having said this, I think it's time to now conclude our lecture with a definition that you must know. The classification from the classification of metamorphic rocks, and that is an important aspect, and I think we have just enough time where we could draw a final conclusion on this term. What is metamorphic facies? So metamorphic rocks are divided in terms of what is called metamorphic facies. Facies, the spelling is F-A-C-I-E-S. F-A-C-I-E-S. So it is called metamorphic facies. Metamorphic facies. Now the definition is, what is metamorphic facies? The metamorphic facies is classified in a pressure temperature field. in a pressure temperature field. Yes? So, metamorphic facies means a rock. So, there are, when you have reactions, obviously the reactions occur along certain boundaries. Say, for example, I think you know this temperature and this is pressure. I think by this time you know about what is called andalusite, sillimanite, and kyanite, all having the formula Al2SiO5. Al2SiO5. Al2SiO5 polymorphs, kyanite, andalusite, and sillimanite, and this temperature and this pressure, this temperature is roughly about 505 degrees centigrade, and this pressure is about 3.7 kilobars. Now you see, between kyanite and sillimanite and andalusite, there are three boundaries. This is where sillimanite is stable, this is where kyanite is stable, and this is where andalusite is stable. So metamorphic rocks, all these are metamorphic minerals, generally found in metamorphic rocks. So if I have to label, find out the metamorphic facies, I have to, if I divide this on a pressure temperature diagram, I will have a network of reactions. So one reaction means a particular PT condition. So a PT field need to be divided into certain grids, and in each grid represents a particular facies. That means, or say for example, the name of the facies is amphibolite. Say, it's not right. Lay the facies is amphibolite. So, all rocks metamorphosed at this PT condition belong to the same metamorphic facies. Have you understood? So, all rocks, equilibrated or metamorphic rocks formed in this pressure temperature domain are thought to belong to one metamorphic facies, and the name of the metamorphic facies is amphibolite facies. So metamorphic rocks are classified according to metamorphic facies. Now this is fairly complicated, but I will draw to you a simple one. I will not try and make it more complicated than what it is. I will try to draw this diagram. Temperature 200, 400, 600, 800, and 1000. This is temperature in degrees centigrade. And this is roughly 20 kilobars, and this is roughly 10 kilobar. And so this is 15 kilobar, and this is 5 kilobar. In this temperature range, so I take this, and I draw this, and I draw 200, 400, 600, 800, and 1000, and I draw a line which joins. Now, no metamorphic rocks form here. No metamorphic rock forms here. Now, first let me draw, and then I will tell you. Now I gave certain names to this. These are all facies: zeolite, PP, BL, GR. Now I will give you the abbreviations of this. Z is called the zeolite facies. PP is the name of two minerals, prainite and pampelite facies. BL is blue schist. And GS is green schist. And EA is epidote amphibolite facies. Now, I won't go into the details of this phase diagram because I think if I have to talk about it, I have to talk in much more detail for you to understand what it means. So, but I will give you this because this is what is the classification of metamorphic rocks. Only I will tell you that there are two lines here which I need to draw. One is a line, just to give you a reference. This is your triple point diagram. Andalusite. Here it is sillimanite, and here it is kyanite. This is for reference. And I will draw one more line to it. This is the granite wet melting curve of granite. On this it is melt, on this side it's granite. This is the diagram that I started with. So this is all that I will say. This is only for your reference. This is the, in blue, you have Andalusite, kyanite, sillimanite, triple point. It's a good reference frame. And this one with a black line is the PT loci along which a granite where XH2O equal to 1.0 melts. That means this is the wet melting curve of granite. The dry melting curve of granite turns to the right, as I told you. Now, here in red are all metamorphic facies. You have to sort of understand, know this diagram, because this is the facies classification of metamorphic rocks. I will not go into details because details means it will be too much details. So I don't go into that. This is called the zeolite facies. This is the most low pressure temperature phases that you get. Then you have, as you go up this direction as you go up, and then you can go this way. You have three parts. This is where pressure increases rapidly. So this is high P by T path. This is low P by T path, and this is intermediate P by T path. So if you go along the high pressure path, then you will get zeolite at greater depth, peridrite, pumpelite at greater depth, blue schist at greater depth, higher depth, you will get eclogite facies soaks. But if you go along the low pressure by temperature path, then you first get zeolite facies, then you get green schist facies, then you get amphibolite facies, and then you get granulite facies. So this is the path if you have a low pressure trajectory, if the change in temperature is at low pressure. Low pressure means it's not greatly above not much below the Earth's crust, Earth's surface, not much below. And this is where the high pressures generate. And then you have the intermediate pressure path. This is called, and you will first get zeolites, then you will get green schist, then epidote amphibolite, then amphibolite, and then granulite facies. So this is the most commonly encountered path, is the intermediate pressure temperature path, where you get transition from, you can see, kyanite to sillimanite. This path is also called kyanite to sillimanite path. And this path is called andalusite to sillimanite. This is kyanite to sillimanite. And here you get andalusite to kyanite. These are the three paths. These are called baric type of metamorphism. Baric, B-A-R-I-C, baric type of metamorphism. So you have the low pressure path, low pressure divided by temperature, low pressure path. You have the high pressure path. This is typical in subduction zones. This is a typical in upper crustal zones. And this is an intermediate pressure temperature path where you will get this. So here you get andalusite to kyanite transition. Here you get kyanite to sillimanite transition. Here you can get andalusite to sillimanite transition. These are the paths that you will get. So in this path, high pressure path, you're not expected to get melting normally. Okay, I think I will stop here for today, and I think I have finished the metamorphic aspect here today. I will not expand on this because it will be too much for you. Right, next we will take up in the next set of 4 slides. I will try to tell you a little bit about structures, folds, faults, etc. And then we would sort of conclude it. Thank you.